All right. Welcome everyone to the January 28th ProfessionalVMware.com vBrownbag. Tonight we're talking Docker with Scott Lowe. And just some quick show notes. So of course you can join in on the conversation using the vBrownbag hashtag. You can also ask any questions or leave comments inside the GoToMeeting window. Remember, we have other podcasts going on globally, so check those out. And you can also download via iTunes or directly from ProfessionalVMware.com. Tonight, again, our guest speaker is Mr. Scott Lowe. You can find him on Twitter at Scott_Lowe. I'm your host, Ahmad Yunus, at Ahmad_Yunus. And with that, Scott, you are now the presenter.
All right, great. Thanks, Ahmad.
Yep.
So let me go ahead and bring up the presentation. I'm listening to you start the podcast here, Ahmad, and I realized, I didn't bother to put in an introductory slide in here about telling about myself. I've been so focused on the content, making sure that I had some good stuff in here. So anyway, thanks for the introduction. My name is Scott Lowe. I've been in the IT industry for quite a while. I currently work at VMware in the Network and Security Business Unit, so I'm focusing on NSX and specifically NSX in open source environments. So I spend a lot of time working in things like OpenStack, Open vSwitch, Docker, related technologies, and really appreciate the opportunity to join you guys tonight. I hope that what I've put together, I was given a pretty broad sort of picture by Jonathan when he contacted me some time ago saying, hey, we'd love to have you follow up on Docker. So I watched last week's show with James Turnbull, which was fabulous. James is an awesome presenter. And he gave you guys the lowdown on Docker. And so I'm not going to spend a lot of time on Docker per se this week, but instead we're going to talk about kind of what happens when you add Docker to something else. And we'll talk about the various something else's along the way. Feel free to ask questions anywhere along the way. I know this is, a little weird because it's not live. I mean, it is live, but you're not sitting in front of me, so I can't see that, hey, I have a question. But just jump in. Ahmad will interrupt me if necessary, and we'll be pausing periodically for questions. It's a mix of demo and presentation, and if you guys have any questions, then just let us know. We'll do our best to answer those.
Sounds good.
So what we're going to be talking about tonight, as I mentioned, James did a fabulous job of giving you guys the basics of Docker on last week's presentation. If you haven't watched that, I highly recommend you go and get it and watch it. I've known James for a while, and he certainly knows his stuff, so he did a great job there. What we're going to be looking at tonight kind of builds on top of what he talked about last week. And so first I'll talk about this one trend that we've seen, which is the rise of container-optimized operating systems and what that means, and then we'll focus in on specifically one example of a container-optimized operating system, which is CoreOS. So we'll look at using Docker with CoreOS. Not included in here, but I'll probably also do is take a quick look at using Docker with Fedora Atomic 21, which is another container-optimized operating system. From there, we'll do a quick break for questions. Then we'll move into looking at using Docker with OpenStack Heat and how we can use the OpenStack orchestration service to schedule and place Docker containers on instances running in an OpenStack cloud. And I'll give you guys some kind of pointers there in terms of things to watch out for. And then finally, we'll come back to looking at using Docker with a tool called Fleet, which is part of CoreOS. It's not necessarily tied to CoreOS, but distributed with CoreOS, and it provides you a little more flexibility in scheduling Docker containers onto a cluster of systems. And I'll have demos along the way for every one of these things, and again, I'll be pausing so that Ahmad can bring in any questions or anything of that nature. So if you want to follow along, there's a GitHub repo for this session. Probably should have included the URL for this GitHub repo on the slide, but it'll be a live clickable link on the PDF that gets distributed. Not that it'll help you guys right now, but if you want to follow along immediately, then just visit my GitHub page, which my GitHub username is LoweScott. So you can just go to github.com/LoweScott, and you'll see a GitHub repo called 2015 vBrownbag Docker, and in that GitHub repo, you'll see some sample files. So in there are some sample systemd unit files for use both with and without Fleet. So if you wanted to deploy a Docker container using one of these systemd unit files, then you could use one of these as an example for moving along. I've included some sample cloud config files for use with Cloud Init. If you're going to be deploying CoreOS on either OpenStack or Vagrant, I'll be using OpenStack in tonight's demos, but there is a great set of tools for using Vagrant if you'd rather do that, or if you don't have access to an OpenStack cloud, which I'm sure a lot of you probably don't, then you can use Vagrant, and I'll try and provide some of those resources along the way so they get captured in the recording. I also have some sample OpenStack heat templates for deploying a CoreOS cluster, as well as the heat template for deploying a Docker container, and I'll be using these. Well, the Docker container template, I'll be using that in the demo. And you'll also find the content source for this presentation in Markdown available as well inside the repo. And as time goes on, if you guys want to star that repo so you have a bookmark for it, then I'll be adding additional files. I wanted to get a Vagrant file put in here, but I ran out of time, and so I'll probably add that later on. So just stay tuned to that for some additional resources moving later on. All right, so let's start with just talking about some of these container-optimized operating systems. And what we're talking about here is that once Docker picked up, we started seeing some operating systems show up that were really optimized around the use of containers. So they, not your sort of traditional Linux distribution like a CentOS or an Ubuntu or any of the variations, but a distribution of Linux that is typically slimmer. So it typically has less stuff in it, fewer packages, fewer features that are packed into it. They typically will focus on a smaller footprint. They'll focus on some other features that you wouldn't typically see in your normal sort of Linux distribution. Some of those things might be automatic updates, for example. They might have methods for doing a rollback in case an update fails. So, like an A/B system partition where it updates one of the two partitions and then reboots on the new version. If it boots up successfully, then it's great. If it doesn't, then it falls back and boots from the old one. For example, and we call those atomic or transactional updates. They'll typically come with Docker pre-installed, and they may have some additional container-specific tools or features. 3 of these come to mind. There are probably more, but these are the 3 that I'm most familiar with. First is CoreOS Linux. This was one of the early container-optimized operating systems. It is slimmer. It provides an auto-update system. It provides that A/B mechanism for booting, so it does an automatic update and then tries to reboot and boot off the updated partition, and if it fails, it'll roll back. It comes with Docker pre-installed. It also comes with some additional tools that CoreOS, the company, is packaging, and those tools would include things like etcd, which is a distributed key value store, and something called Fleet, which is a primitive scheduler. They have another project called Flannel, which is a container networking tool, and all of these are projects that they're pushing forward. Another is Project Atomic, which is a Red Hat kind of sponsored project. So you'll see atomic versions of Fedora, and I'll demo that tonight. Atomic versions of CentOS and an atomic version of RHEL. And these, again, are slimmed down versions of those Linux distributions. They focus on transactional or atomic updates, which is one of the names. There are new tools all around that are emerging, RPM-OS tree, for example, that are emerging that will help do a transactional system update, so you don't update the individual package, you update the entire system as a whole. One of the most recent introductions in this space is Ubuntu Core. I can't really figure out whether Snappy is part of the official name or whether they're just calling it that. I think it's actually part of the name because they also changed their packaging format. And so you use a tool called Snappy to install packages. Again, this is a container-optimized version that they have going on. So what I've got, and I'll show you guys this real quick, is I have a, this is my OpenStack portal. So Imad, can you guys see this okay?
Yeah.
Okay. So I've got in here some instances that I've spun up in advance for the demos, and you can see I've got and actually a couple of different operating systems in here. So I have an instance of CoreOS, the most stable release, which was just updated to include the glibc fixes, so CoreOS 522.6.0. I've also got a copy of Fedora 21 Atomic that we're running, and I'll log into each of these in just a moment to kind of show you a little bit of what's going on. I don't want to spend a whole lot of time on those because I want to get into the more important stuff later on with Docker, but I do want to show you, for example, I've got these running, and I'll talk more about these guys down here, these other nodes, in a little bit. So I would imagine that you'll probably see other container-optimized operating systems emerge. I don't think this is the end of what we've seen as far as any predictions on which one of these will end up being sort of the predominant one. It's too early to say yet. I'm most familiar with CoreOS, and so I'll use that pretty extensively tonight in demonstrating some of the things with Docker. But by no means is that an indication that they are the best or anything of that nature. It's just the one that I've had the most experience with. So when it comes to using Docker with CoreOS, as I mentioned, CoreOS being one of these container-optimized operating systems that comes with Docker pre-installed. So let me flip over to a terminal real quick. And we're just going to SSH into one of my systems. And this is a CoreOS system. So I just spun this up not too long before the presentation started. And so I haven't done anything with it, but we can see if we run which Docker, we can see that Docker is already installed, and I can run a Docker version and see that this particular build of CoreOS comes with Docker 133. And so I could, go ahead and do any of the normal sort of Docker type things that I would want to do. So if I want to see if there are any Docker systems running, I can run a Docker PS. You see there are no containers running. And if I wanted to look at what images might be preloaded here, I can run a Docker images and see that there are some Nginx images that I've downloaded, and I downloaded them in advance just to avoid you guys having to sit there and watch it download, which obviously doesn't really help you guys at all. I mean, if I wanted to run one of these Docker images, then I could do a Docker run, and much in the same way that you saw described last week with James, and then run one of these guys. And so I won't bother with that right now because that's fairly straightforward. But you can see this is straight out of the box, spun up off of the OpenStack image that CoreOS provides, which is a QCOW2 disk image, uploaded into OpenStack and then spun up, and that's it. And no customization or anything of that nature. It's just straight out of the box. Now, by default, out of the box, Docker isn't running. So CoreOS uses systemd on the back end, and so if you wanted to see the status right now, it's running because I started it. But when you first boot up a CoreOS instance, and the others may be the same, this is just the example that I have here, Docker would be stopped and you'd have to start Docker. Then you can see some of the command line variables and such that are used there for this particular Docker service. Now normally, flip back to the presentation, normally, or should I say typically, you would use a systemd unit file to run your Docker containers as a back-end service. And so this is it's a systemd thing, and I don't want to get bogged down in the religious debates about whether systemd is the right architecture or not. But that's what CoreOS uses, so we'll just take a quick look at it. But you can see here it's fairly straightforward. The key parts to look at the bottom are this exec start pre, exec start, and exec stop. And that exec start pre just says before you actually start the service, I want you to go and run a Docker pull to get the latest Nginx image from the Docker registry. If you were running your own internal private registry, then you could specify that you wanted to pull from the private registry, which would avoid you having to download the image across the internet. And you might not need to do that if you were sort of pinning your container to a specific version of the image. This just says the image, so it's going to assume the latest version of the image. If you wanted to tie your service here to a particular version of the Nginx image, then you could specify a particular version just by appending that exec start command where it says nginx with a colon and the version number. And if I flip back over to the demo, you can see I'll run a Docker images again. And you can see I could just look at, say I wanted to run, 1.7, I could run nginx colon 1.7, and that would specify the 1.7 version of the nginx image. Latest is just a pointer that points to the latest version. And so once you create the system to unit file, and there's a copy of the system to unit file that you see here in the GitHub repo that you can pull out and use. This particular one runs a standalone instance of nginx and just maps it to port 80. And so you could then use systemctl to start this. Now I didn't actually copy the systemd unit file into the right place in CoreOS because I just spun this instance up. So I'll manually run the command that you see down there, and that way you can see Docker running. So let me just do that real quick. So I'm just going to do a Docker run. And then here, if I wanted to tag it to a specific version of the image, I could do something like this, like 179, but I'll just leave that off. And then when I run this, then, oh, I missed a dash, but that's okay. Now you see like it kind of looks like it's locked up right here. That's because I didn't tell the Docker daemon to fork that container off into the background and return me to my prompt. So my prompt here is actually kind of subsumed by the Docker container right now. So if I flip back over here and we'll create a new tab, I can actually go to the address where this VM is being hosted, and bam, there's nginx, right? Standard plain Jane, ordinary welcome page. And then if I go, and you can see here, it's logging to standard out, and so you can see that I accessed that web page from my local system, and it gives you all that information being logged right here to the screen, so you can see that it is actually working. So this is an example of a Docker container just being spun up on CoreOS. Now again, typically what you would do is you would create the systemd files. Go ahead and stop that. There we go. Typically you would create the systemd files like shown here, and you would install them onto CoreOS, and then you would be able just to run a systemctl, and it would run this as a daemon. And that's one of the reasons why the command that I ran didn't fork it off in the background, because when it runs by a systemd, it has to run in, systemd will take care of it being a daemon in the background. So you want the command to actually run foreground, and it'll take care of all that. And so you would normally put these into a systemd unit file, copy it in the right location, run the necessary commands. That's all pretty well documented by CoreOS. And again, I didn't want to get too much into the specifics of CoreOS, but just to give you an example of how some of these container optimized operating systems are shaping themselves around the concept of containers. And CoreOS is really this way. Almost everything runs as a container, and so you really don't have any services or daemons that are running outside of containers. Now let's take a quick look at Project Atomic. So I'll log out of this one, log into my Project Atomic host, and again, this is just spun straight up from the Fedora 21 Atomic image that they make available. Docker is pre-installed. We can run Docker version. It shows that it's running here. We can run Docker PS. I'm now going to deny there because I'm not don't have permission to hit the socket where it's listening. So Docker PS shows that there are no images running. Oops, helps to type correctly. And then here shows that I've downloaded some images again. And I could run the same sort of command. Oops, sorry. And then just mapping the ports. Oops, helps to be sudo again. There we go. And then again, now I'm still pointing to the old one. If I try and refresh this, it'll give you an error because we killed that container. That was on the CoreOS box. And then here again, now we're running on the Fedora box. And again, you can see it being logged out to standard out to show that I was indeed actually accessing it. It wasn't just some sort of trick that I was playing with you guys. So I'll kill that. And we will log out of that back to my system. And we'll go back to the presentation. All right, so that was the demo that I just showed you. I'll stop here, and Imad, let me know if there are any questions coming in from the audience.
Currently, no questions.
All right. Either I have bored them all to death in their sleep, or we haven't gotten deep enough yet. So let's go a little deeper. Let's talk about using Docker with OpenStack Heat. Now, for those of you that maybe didn't follow along in the Couch to OpenStack series that vBrownbag ran, Heat is an orchestration service for OpenStack. And what that means is that it allows you to create instructions or templates that will automate the deployment or creation or provisioning of any of the various services that OpenStack provides. So in a very basic OpenStack installation where you have compute instances and networking and storage, then Heat templates can automate the provisioning of networks, network topologies, logical routers, instances connected to those networks, storage volumes, and it can orchestrate the placement of Docker containers if you have the Docker plugin for Heat installed. So you have to install the Docker plugin for Heat in order for it to work. And then once you do that, then in your templates, you can also deploy Docker containers onto instances inside your OpenStack cloud. Now there are some caveats, some gotchas, shall we say, when you want to do this. Now my OpenStack cloud is a slightly older release. I haven't upgraded it for a number of reasons. Time is one of those. And so it's running Icehouse. And in the Icehouse release, the Docker plugin for Heat was essentially broken. It just didn't work. And in order to make it work, you had to really jump through some hoops. You couldn't use the stable Icehouse release of the plugin. You had to move to master. And then you had to edit the file to a certain place, because if you didn't edit that, then you would have had to take Heat to master as well. And if you took Heat to master, then there could have been issues with Heat interacting with all the other parts of OpenStack. So it's reasonably well documented how to make it work. And in Juno, it's better. So it's not quite as broken, a little easier to get up and running and a little more stable. The other thing that is something to be aware of is that you have to make sure that your Docker endpoints, and I'll talk a little more about those in just a moment, they have to be reachable from the server where Heat is running. Now Docker, as you may already know, by default Docker listens or works off of a local Unix socket. So there'll be a file that it attaches to, and if you want to subscribe to the actions the Docker daemon is taking, or if you want to manipulate the Docker daemon, you have to have permissions to modify that file. And you can't remotely control that file. You have to actually reconfigure Docker, and it doesn't work this way by default, but it can be reconfigured to do that. You have to basically reconfigure it to listen on a network port instead of a local socket. And I'll show you how that can be done in some automated ways. But when you do that, you also have to ensure that the network port, the IP address and port that Docker is listening on, is reachable from the server where the Heat services are running. And that has to ensure that if you are, for example, using an OpenStack environment where tenants can spin up their own networks and just assign addresses willy-nilly because it's all isolated using overlays or some other form of technology, you have to assign floating IP addresses, or you have to do some routing changes or something of that nature, but you have to make sure that, one, it's reachable via regular IP connectivity from an IP addressing perspective, using floating IPs for routing or layer 2 bridging, whatever the case may be. And two, you have to make sure that your security groups allow that traffic through, because by default they won't. And I'll show you more details on that in just a moment. The last caveat to be aware of is that you don't get any intelligent placement of the Docker containers. Now this will make a lot more sense when I actually show you the template that spins up a Docker container. but you basically have to hard code the endpoint, the Docker endpoint, so the IP address and the port number, where you want that Docker container spun up. And if you don't, well, then it doesn't work. And so the problem with that naturally is that when you hard code that endpoint into a template, if that endpoint ever goes down or ever changes, the template has to change. So there isn't any sort of intelligence in saying, I want to deploy to somewhere within my data center, and you pick. You have to actually say, I want you to deploy to this specific host. And so that does limit the effectiveness of the Docker plugin for heat somewhat, in my opinion. So enough talk. Let's look at the demo. So I'm going to flip over to my OpenStack dashboard, which is here. And to kind of illustrate the point that I was making earlier, so I have these two instances, this CoreOS Solo and Atomic Solo. These are both sitting on a private network. And so if I go down here, networks, you'll see I have a network called LabNet, and it's got a 10.1.1 address, which is not reachable from the rest of my home network. It's an arbitrary network. Now this OpenStack Cloud is being powered on the back end by VMware NSX. So NSX is handling all of the networking for the lab. So when I spin up these instances, in order to make them reachable from the outside, I had to assign floating IP addresses. And these floating IP addresses are reachable from my home lab. And so that's the sort of thing that you have to make sure is if you're going to deploy, if you're going to use the Docker plugin for heat in your environment, then you have to make sure that any endpoints, Docker endpoints, which are instances running the Docker daemon, listening on an IP address and a port, have to be accessible via an IP address that the server running the heat services can access. And so depending on how your VLANs are set up and depending on how your OpenStack controllers are set up and depending on where OpenStack Heat itself, which is a couple different services, depending on where that's running, you may have to ensure, you may have to allow firewall rules, you may have to ensure that network address translation is occurring or not occurring, that sort of thing. You just have to ensure that you've got the right level of IP connectivity between the heat server and your endpoint. Once you do ensure that and you have everything up and running, you'll have a section inside OpenStack that looks something like this. This is the orchestration environment. You can see I've already got one stack, which is a template of pieces put in here. And this is a cluster of CoreOS nodes, and I'll come back to that in a little bit because we're going to use that for our heat demonstration. But this spins up a bunch of pieces. Let's actually take a look at a template. And you can get this, I'll have to escape out of my piece. You can get this from the repo if you want to look at it. That is probably not very readable. How's the readability on that, Imad? Do I need to up this font size a little bit?
I can actually see it pretty good.
Oh, okay. Well, then we'll leave it be then. So this is an example of a heat template. This is obviously a very, very simple heat template, but this is an example of a heat template. And what we have here is it spins up a single image. So first we have our line that tells it the heat template version. This is all documented on the OpenStack website, by the way, and I've got a number of blog posts out that talk about how to use OpenStack Heat and looking at templates and that sort of thing. So there's additional content that you can find for that. Then you have a description, which is just a human readable description of what it is. Then we go into the resources section. The resources section is where we actually define the resources that the template is going to create. And in this case, we have a single resource called Nginx-01. We have the type, and this type is a specific thing that you have to run, which is the Docker Inc, : Docker, : container. And then you get into the properties of that particular type of resource. And in this case, we have an image name, which it just defines as Nginx, a Docker endpoint, and you'll see here that we're referring, again, a specific IP address and a specific port. So you have that particular IP address, and in that case, it's one of the CoreOS nodes in my cluster. If that particular CoreOS node goes down, this template will fail to work. I can't just sort of redeploy the template and have it pick up the next available host. It is hard-coded to that particular IP address and port. So I have to ensure that IP address is reachable from my heat server, and I have to make sure that my security groups are not blocking the particular port number. Then we have port specs, which just says that the container listens on port 80, and then a port binding, which says bind the host's port 80 to the container's port 80, so that you can pass traffic all the way through. Very, very simple template. It assumes the presence of the underlying networks. It assumes the presence of the underlying instances, which are provisioned by these IP addresses. So, all it does is say, I'm going to go hit this IP address, and if that IP address doesn't exist, it'll just error out. It'll give you an error and fail. So let's run this. Before I do that, let me log into the host where this Docker container will end up. All right, so I'm running another CoreOS node. This is actually a node in a cluster. And I'm going to run a quick net stat to show you the listening ports. Draw your attention to the fact that we're listening on port 2375. This is the official Docker port as assigned by the IANA. And I have modified CoreOS to actually listen on that port. The default is not to listen on that port. The default is listen on the local socket. So I actually have modified it to listen on this port so that we can use the heat plugin for Docker to actually orchestrate something. And if I do Docker PS, you'll see that there are no images actually running. There are no containers running right now. And if I do a Docker images, you'll see that I have pre-downloaded a bunch of images so that when we run our template, it won't sit there for a couple minutes doing nothing, apparently doing nothing, while it's actually downloading images in the background. That's just to make the demo a little smoother. You don't have to download the images in advance in order to use the template, although that was a problem on one of the early versions of the Docker plugin, is that it didn't understand how to go get images if they didn't exist. But if you are running a recent release of OpenStack and the Docker plugin, then it should be fine. And it will pull images down automatically if it doesn't have them. I just simply preloaded the images here to be sure that the demo didn't sit there and stall and we're all twiddling our fingers waiting for this thing to actually do something. All right, so let's go back over here, and we're going to go ahead and launch the template. So I will just point this thing to the template that I showed you. And I don't need any additional environment variables, so we'll leave that blank. It'll ask for a stack name, which is just a name for you, and it will ask for the username of the password of the user, and then we'll say launch. And you'll see, okay, Docker simple, it's running, it says it's in progress. It'll sit here for a little bit, 30 seconds, okay, maybe less than that, and then it'll say it's complete. And you don't see anything, right? So we go back over here to compute instances, and there's nothing new listed here, and that's because OpenStack itself is not container aware. It has no concept of containers. That is something that the OpenStack community is currently working on through a project called Magnum, but it's not there yet in any released version of OpenStack. So it says that it worked, but we don't see anything in the GUI, right? In order to actually see what's going on, we have to go over here to our host that was targeted, and we'll run a Docker PS again, and now we see that whereas before there were no Docker containers actually running, now we have a Docker container that is running, and you see that it's up, it's listening, it has ports that it's mapped out. We could now take this IP address, plug into another tab, and we would see, bam, there we go. Now we're running the Nginx piece again. And so it works, right? It does deploy an image. You can deploy multiple images. You could specify where you want them placed by specifying the endpoint. It will download images and it'll run them. It'll map the ports that you need mapped, all of the things that you normally need to do. But as you can see, it's not very flexible. There's no representation of the containers inside OpenStack itself. It's very rigid in terms of a container being tied per the template to a particular endpoint. And in order to manage it, you have to drop back. Now, I've actually set it up, because this is listening across the network, I'm going to log out of here back to my jump host, And I will actually, I'm going to show you, I'm actually going to use Docker remotely. Now, a lot of people don't know that you can use Docker remotely. It's a single install. It's like one binary that is both client and daemon. And by default, the client looks at the local host. And by default, the daemon attaches to a file on localhost. So you can install Docker on a Linux system and run Docker commands. And assuming you have permissions, you have to run a sudo. You can run Docker commands, and it just works because the client points to localhost, the daemon points to localhost. Everybody's great. Because we had to configure Docker to listen remotely in order to use it with the Docker plugin for heat, this also means that I can go to another system, install the Docker binary, and actually use the client side of Docker to connect to the server side of Docker on another host to look at things. So I made some files just to make this easy so that you can see some of the variations of what's going on. And we'll come back to these again when I do the next demo, which is Fleet. But I'm just going to source this file real quick, and then I'm going to run Docker PS. And notice that what I've done is I've exported an environment variable called Docker_host, and I've given it that TCP endpoint. So it's the same IP address and port that we saw in the template earlier. And so now when I run Docker, then what's going to happen is Docker is going to use that endpoint, that host, as the place where it's going to go. So when I run Docker PS, it's going to go connect to that CoreOS instance and show us the same results we saw if we were logged in locally to that CoreOS instance. So this gives you some flexibility in that you can install the Docker binary somewhere else. I've heard some people installing it on their OS X laptops, for example, and then connecting to their Linux systems on the back end because they configured the Docker daemon to listen over the network. It also means that I could do various things like kill the image and download new images and that sort of thing. All the various things that you would typically expect to see, right? You can do remotely. Now, if I want to kill this thing because, okay, I've seen enough, great, that's fine, whatever, we can go back to our OpenStack dashboard, and I'll just leave that open. And here's our stack. We can just do a delete stack, and it'll confirm. And you'll see that it says it's done. Little sort of feature here in the UI that it doesn't remove this. If I go to stacks again, now it's removed. And when I go back to my jump host here and I run Docker PS again, you see that now it's gone. And so what you've seen is the heat plugin for Docker, or the Docker plugin for heat, depending on how you want to look at it, talking to the Docker daemon on that particular instance to coordinate whatever it is you want to do. And this is a very, very simple example. It's a single container running Nginx with simple port mappings, but what you can do with the Docker template, or the heat template, excuse me, is obviously far more complex than that. I'll show you an example of a more complex one in just a moment. But before we get to that, let's take a quick look at how you would go about configuring CoreOS as one example to listen over the network. Remember, I mentioned that by default, Docker listens on a local socket and doesn't listen over the network. And so you have to configure it to listen over the network. And in order to do that, one of the most common ways of doing that, especially in a public cloud environment, is to use a tool called Cloud Init. Cloud Init is designed to customize Linux instances when you boot them up in a cloud environment. And to use Cloud Init, we use a cloud config file, which is similar to what you see here. And using this cloud config file, you can customize the behavior of the Linux distribution that you're spinning up. Now, in this particular case, I'm using CoreOS, as I mentioned, and so I have some CoreOS specific features here that we can embed inside our cloud config to actually customize it. So when we spin up a CoreOS instance, it will automatically customize that for us to do whatever it is that we want to do. So one of the first things it does is it sets some values for etcd. I'll talk more about etcd in a minute, but etcd is a really powerful distributed key value store. Okay, it sets some values for that, and then it goes into the units values and it tells it to start etcd and start service, and then it creates this system called Docker TCP.socket. And then you see under the content section, it actually writes out a systemd unit file. In this case, it's a socket file that tells systemd that the Docker service, okay, which is indicated by this line right here where it says, Docker service. The Docker service should listen on this particular port, 2375. And so when you spin up a CoreOS instance, for example, and again, this is CoreOS, but similar sort of mechanisms could be used with Ubuntu, with Atomic, with non-container optimized systems like regular Fedora or CentOS or RHEL. The documentation for the cloud init settings that they would use would be specific to them. But when you run this, when you use this piece to spin up, then it'll automatically customize that when it boots up. So let me just, I think I've got time to actually demo that for you. So let me actually show you what this looks like. I'm going to copy all this to my clipboard. I'm going to flip over here and we'll actually spin up another CoreOS instance. Okay, CoreOS demo. And I will pick how much resources I want allocated. I'll pick my image. Okay, you can see I've got multiple versions in there. I'll pick which key pair I want in there, which security group I want in there. I will choose which network I want it to attach to. Let's go ahead and put it on there. That's fine. And then here under post creation, it says it's a customization script. And over here, you'll see where it talks about analogous to user data. This is where we're actually going to paste the contents of that cloud config file. And so as I scroll back up through here, then you can see this is the contents of the file that we were using earlier, right? So then I'll just say launch, and it will spin up a new system. It'll take a little bit because it might be spawning onto a hypervisor that doesn't have that image already downloaded. Okay, there it is. See, it's giving an IP address. To make it accessible from the outside, I'm going to go ahead and add a floating IP off of a routable address. So I'll just do that real quick. So now this instance will be available on this IP address, and we can take a look at the console to see when it's done booting up. Whoops. There we go. Okay, so it's done booting up. Let me go back to my other window. There we go. Okay, so now it's done booting up, and I can go to my piece, and let's say we want to SSH to that. We specify the key that we provided. Username is core. They give us 103. Yes, bam, there we go. Now we see it got the name that I provided, CoreOS demo, right, which is the name I provided when I deployed it. And if I do a netstat, helps to type correctly, you'll see that it's actually listening on 2375. So that tells you that that customization actually caused the Docker daemon to listen on the network port as we instructed, rather than listening only on a local socket. All right, and I can show you just for demonstration purposes. We go back to the other system where we did not apply this, I don't think. I don't know if I remember if I applied it here or not. Okay, you can see in this case I didn't apply the configuration script, and so Docker is listening only on the local socket, not on a network port. All right, so that file is in the GitHub repo, so you can use that to your heart's desire. And let's go back to our presentation. All right, I will stop here before moving on to the next thing. Ivan, do we have questions?
No, I think you've melted some minds right now, so there's no question.
Oh, okay. Yeah, there you go. All right.
By the way, the depot, I tweeted that out earlier, so people should be able to see that using the hashtag.
Oh, awesome. Okay, great. So you tweeted out the URL for the GitHub repo on Twitter.
Yes.
Using the vBrownbag hashtag.
Mm-hmm.
Perfect. Okay. So if you guys need to get that URL, then go check Emad's tweet stream, and it's there. Or look for the vBrownbag.
Just use the vBrownbag hashtag, yeah.
There you go. All right. So last thing we're going to talk about, and then we'll wrap up, is something called Fleet. So we're going to look at using Docker in conjunction with Fleet. Now, Fleet is an open source project that was sponsored and as far as I'm aware, started by CoreOS, the company, and it is distributed with CoreOS Linux, the product. And what it does is it takes systemd, which is the init system that they use in CoreOS, and it ties it together with etcd, which is a distributed key value store, and allows you to schedule systemd units onto a cluster of systems so that if a system becomes unavailable, then you can simply deploy to another system in the cluster. So this solution kind of gets around the problem with using the Docker plugin for heat, because the Docker plugin for heat is tied to a particular endpoint. Now what we're doing is we're tying it to an etcd cluster, which may have some number of systems in it, and then between etcd and systemd and the contents of the unit files, I'll show you what they look like in a minute, you'll be able to deploy onto some node in that cluster. Now it does require the presence of an etcd cluster, so you do have to configure etcd to start. I'll show you what that looks like. And you do have to use systemd units to deploy the containers onto the cluster. I have given examples of all of this information on my website. So if you go out to my website and take a look around, you'll see me talking about how to use Fleet and how to deploy pieces onto it to schedule containers onto the cluster. So let's take a look at a sample systemd unit file, and there are copies of these in the GitHub repo that you are welcome to use. You'll see it looks a lot like the one that we showed earlier, right? The key difference here is this section down at the bottom where it says x-fleet, right? And what this is a set of Fleet-specific extensions for systemd that allows us to influence the way that systemd uses etcd to schedule Docker containers onto an available host in the cluster. In this case, we're using the conflicts parameter, which tells it, don't place this service where it might conflict with any other service that has the name nginx-something. Now you'll notice that the name that I've given this, and that's on the exec start line here, is nginx-01. And I actually have two more unit files that are intuitively named nginx-02 and nginx-03, because I'm creative like that. And each of them looks this way with the exception of the name that is found in the exec start and exec stop lines. And what happens is when we submit these files to Fleet, it will look at what's available out there. It will try and schedule them available out there, and then it will use that conflicts line to say, well, I can't put two of these guys on the same host because that will create a conflict. And I'm told that I can't create that conflict. So basically what you're doing is you're forcing these nginx containers to be distributed on different hosts in the cluster, so that it doesn't say, oh, I'm just going to put all three on the same host, which would kind of defeat the purpose of having multiple copies of this container running. This gives you a way to distribute and provide some fault tolerance. Now, there's obviously more involved here. You know, we would have to have a load balancer, right, to take traffic coming in and then distribute it to one of these available web servers, for example. We would have to have some way of registering these containers in the load balancer. So if I decide I need another container, another nginx instance, and I decide to just spin up nginx-04 and have Fleet schedule that somewhere, then I don't want to have to manually go edit my load balancer so that I now show 4 nginx web servers instead of only 3. So there's lots of things going on here. There's various tools that are designed to leverage etcd or leverage other distributed key value stores like Console that will use a variety of mechanisms to provide that automatic registration. This whole process, by the way, falls under the term service discovery and service registration, where when I might be spinning up services anywhere in a group of compute nodes, I need to have some way of discovering where that service is running and registering that service with whatever other services need to access it. So again, I have some systemd unit files for use with Fleet. So now that I have officially brought up the slide, let's actually look at those. So here's one, and it's got a funny thing because Mac OS X thinks that dot service means something other than what I mean it to mean. And so here's the description. It's this one I just showed you on the slide, right? And you can see that I've got 3 of them, here, here, and here. And I can actually submit these to Fleet. Now first I'm going to flip back over to my jump box. Okay, so this is a box just running Ubuntu 14.04, and I've got all the necessary stuff installed on it to do what needs to be done. And that includes a copy of the Fleet CTL command, which we'll use to control Fleet. And as with the Docker command, you can use Fleet CTL on a system other than where Fleet is installed. So in this case, I've taken the Fleet CTL command and I've put it here on this Ubuntu Linux system, and it's actually going to talk to etcd and systemd within a cluster of CoreOS boxes. So actually, before I get into that demo, let me go here to my OpenStack piece, and you'll see I have 5 nodes. Okay, they're not in numerical order. CoreOS node 01 through CoreOS node 05. They have these addresses assigned to them. This is a routable address space being provided by a logical router powered underneath by VMware NSX. And so these addresses are reachable from the outside, from the rest of my home network. And the etcd is running. So they are part of an etcd cluster. They are distributing data. They are talking to each other. Given the time constraints, because I'm almost out of time, I don't have time to get into etcd, but I did do a blog post on it, so have a look at that. But you can see this is here. This whole stack, by the way, was turned up in heat using a template. And so I just took a single heat template and submitted it to OpenStack Heat, and it spun up all the instances for me. And if you would like to see what that template looks like, it is in the GitHub repo, if I'm not mistaken. Yep, it sure is. I had to double check. Okay, so you can always pull that down from the template. Now, just keep in mind when you pull down any of these files from the GitHub repo, there may be UUIDs or other things in there that you're going to have to fix for your environment. Like the cluster heat template that I used to spin up this cluster is going to have UUIDs for my images and my networks, my security groups. They're not going to work straight off the bat in your OpenStack environment. So you're going to have to look up what those environments, what that information is. Okay. So I've got it here. Now I'm just going to check real quick to see if I've got. I don't. So I'm going to set an environment variable real quick that will tell Fleet Control to go talk to the etcd cluster. Okay, and you'll notice that this environment variable points to a specific node. So if this node goes down, you would have to point the environment variable to a different node. That's because we have to have some entry point into the cluster. But we can enter at any node in the cluster. We're not limited to, we have to use a particular one. We could use any of them. All right, and I'll do a Fleet Control list machines. And it will list all the machines in the cluster. So here are the 5 nodes that we currently have in the cluster that I showed you earlier inside the OpenStack dashboard. Okay, and I can do next another Fleet Control command that will show me the units or containers that are running. And basically there are none because we haven't done everything running. Now in this directory, I do not have the images, the instances that I need. So give me 1 second real quick to copy up the source files that I need to copy up. Okay, so I want to take a minute. Sorry about that, folks. Bam, okay, let's see. There they are. And so you can see the Nginx-01 through -03. And now if I wanted to submit them to be scheduled onto that, I would use the fleet control command again, fleetctl submit nginx-star.service. And it comes back and says, okay, great, so let's see what it did. fleetctl list units, still nothing, okay. So let's go ahead and start them or launch them. fleetctl start nginx service. And this will tell it to actually go and launch them. And so you see it's launching on various different systems. And so now when we go back and run a list units, we see that it is running on 3 different hosts automatically. So it has taken the service that was on there and automatically just had communicated with etcd to see who's available in the cluster, communicated to systemd on each of those nodes and saying, I want you to run a new Docker container, here's the unit file, and then use that conflicts line to ensure that we don't schedule multiple instances on the same node. Now, let's see. So just to see that this is working, let's do a source node 01. Node 01 is .18, so if I run a Docker PS, we see nothing, all right? So if I then source node 2, Docker PS, nothing. Source node 3, then again, sourcing these files just means I'm changing an environment variable that tells Docker where to go. I run a Docker PS here. Bam, you can see that I've got Nginx 02 landed on 22, which is there. If I then source 4, run Docker PS, I can see it there. Source 5, run Docker PS there. And so you can see Fleet is just using the underlying mechanisms. It's using Docker and etcd and CoreOS and systemd unit files to schedule these guys onto this. So now it will just automatically distribute them. It knows there needs to be 3 of them, so if one of these goes down, it will actually spin up another one on another available host. And it will do that through some very, very rudimentary liveness checks. Like, it's not super intelligent. It just checks for periodic updates to some keys inside etcd to see if it's still there and running, and then it goes from there. But that gives you an idea of how Fleet works. Unfortunately, Fleet has no integration into OpenStack or anything of that nature, so even though I've distributed these things, if I go back to my OpenStack dashboard, you'll see I still don't have any notion of where this is running. It's not integrated into Heat, so it's not going to show up as a stack. It's not integrated in the instances, so I'm not going to see anything up. In order to see it, I actually have to go to that command line and run fleetctl list units, and it'll show that they are then running. And if I wanted to, I could go over here to Nginx, and I could change this address. Let's say we saw it scheduled on the 19, okay, bam, and we saw it scheduled on, if I run it on 18, we should get in it. I think the container might still be running on 18 that we haven't shut down. Let's try 21. Yeah, 21 gives us an error because that's one of the nodes in the cluster that doesn't have a container running on it. All right, so I know we are just about out of time. Ivan, any questions?
We actually have one from Twitter, and it was, what kind of hardware are you running this on?
Okay, so not about the demo, but about the hardware.
Yeah.
It's actually it's old equipment I bought from a company going off lease. If you time it just right, there are waves of hardware that will get into the corporate data centers on lease, and then a few years later they'll be coming off of lease, and the companies will need to sell them and replace them and under lease contracts, all that kind of jazz. And so you can find these guys super cheap. So I actually have a pair of Dell C6100 servers. These are 2U, 4-node, each per 2U systems. So 8 cores and 24 gigs of RAM per system. So 8 of those running OpenStack Icehouse with Ubuntu and KVM and VMware NSX for networking. And then I've got a Brocade core switch and a Synology on the back end for some storage, although most of the storage is local. So.
Wow.
But you could do a lot of the stuff that, except for the OpenStack stuff, which is, you could do that. You could run something like a DevStack, which is a very simple single node installation of OpenStack, along with a CoreOS cluster under Vagrant on a local system. So if you have a local laptop and then your laptop has 8 or 16 gigs of RAM, you could run. You didn't necessarily need the OpenStack stuff because you could see we don't have any visibility in OpenStack on stuff during Fleet, so you could just run a CoreOS cluster, 3 nodes running under Vagrant, and you could do the demo that I just did with Fleet Control. You could submit Docker containers to be scheduled onto this piece, and there is actually a GitHub repository that CoreOS sponsors, and I'll tweet this out real quick. But if you wanted to look at running CoreOS with Vagrant, you could do this. It has a Vagrant file. It has cloud config files and all that stuff to make it easy to spin up your own local CoreOS cluster using Vagrant on your laptop. And I actually wanted to do that tonight, but I ran out of time, and I wouldn't have had time to go through the presentation anyway, so I guess it's okay. All right, so I know we're just about out of time, but if there are any other questions, I'm happy to take those now. So fire away, either Twitter or chat window or whatever.
Chat window is actually clear, and
Okay.
right now Twitter is clear as well. So I think you literally melted their minds.
All right. Well, then let's wrap it up. So if you want to kind of stay in touch with me, so to speak, my blog is at blog.scottlowe.org. I just recently migrated that from a WordPress installation over to Jekyll and GitHub Pages. And so, but all the content there and all the URLs, permanent links were maintained. I'm on Twitter as at Scott_Lowe, as Ahmad mentioned at the beginning of the presentation. My GitHub username is LoweScott, so you could get out there and look at the GitHub repo. Again, Ahmad tweeted that, the vBrownbag hashtag. If you're ever on Freenode, one of the IRC networks, I am there occasionally on as Lowe. I'm very imaginative, I know. And then my motto for life is taken from Colossians 3:17. So that's it. Thanks very much for allowing me to come on. I appreciate it.
Well, thank you. Great stuff tonight.
Thanks.
All right, I'm going to stop the recording.